You are live.
All right, well, welcome back, everybody. So today is our last day on transmission line protection, and as I kind of anticipated after day one, I've got a whole lot of content left, and we don't have a ton of time. So what I want to go over today is wrap up step distance scheme. So we started talking about that last class. Go through a step distance calculation example. Paul was able to get a homework assignment for line protection posted and should be available for everybody. It's going over a similar distance protection calculation assignment. So hopefully everybody should be able to get through that. And we're going to go through some examples today of the calculation side of it. Doing it by hand is a little bit different than what we usually do for actual applications. We're using different calculation tools and Aspen to drive a lot of the data and decisions we're making. But I figured we can go over a pretty basic transmission line step distance protection package today. So I'm going to use the first probably half of the class going over the calculation example, a few other considerations for step distance schemes. But I'm going to probably blow through most of the slides at the end of the slide deck here on some of the more unique considerations fairly quickly, so that we can talk a little bit about pilot protection before we wrap up the transmission line part of the class. So, as always, stop me at any point if you have any questions, and I'll open it up now in case anyone has any questions or stuff that I'd like to ask about what we've gone over the last few classes. All right, well, we might as well jump right in. So last class we talked about step distance protection schemes. They're typically applied as 2 or 3 different zones of distance protection, so impedance-based protection that use a variety of sensitivity set points for coordination and time delays for coordination to provide full fault coverage for the entire length of the line, and coordinate with adjacent protection systems past the end of the line. That's accomplished through underreaching and overreaching zones and time delays to accomplish that. So we've got the basic figure here of a 2-zone step distance scheme with zone 1 an underreaching zone. So it only protects part of the line, but it's able to operate instantaneously. And then zone 2 being set above the line impedance so that we can be sure that it overreaches the line. But because of that, it's going to reach further into the system, and we're going to need to delay it to provide coordination with the remote, bus protection or line protection off the remote bus. So we're going to go into a calculation example. So this is stuff we would be doing on a kind of day-to-day basis as a protection engineer. This is a lot of the work we get involved with is this type of calculation, and we're pulling the information. We need from multiple sources. So a lot of it is going to come from Aspen or whatever fault simulation program you're using. We're also going to pull from line impedance information that is in Aspen, but may also come from other sources, line loadability rating info. We're going to be looking at the drawings, the design drawings, and some supporting calculations to determine our current transformer ratios and what the PT ratios are for the actual connections, sensing connections to the relays. And that's the information we're going to use for the basis of the calculations of our set points. So I've got some pretty typical information here of what we would start with in a line protection application calculation. So we've got the line data, which would come from Aspen, and in this case, it's per unit quantities on a 100 MVA base. And we've got the positive sequence, Z1 here, and the zero sequence, and that's set up in a R plus JX format, which you're all familiar with. And that's what you'd see if you open up the line window in Aspen. It's going to show you this information. In our case, we've got a single line modeled from one end to the other, so this information's all together. But if you had tap buses or other things in the middle of the line, you'd have to, you'd be looking to really find the impedance of the line from terminal to terminal. So if you had a tap station or another tap bus or switching station or something in the middle, but the protection is bounded by the breaker locations, you'd have to add up all the the impedances to get from one end to the other to come up with your full line data. So really what you're looking for is the impedance from this terminal to the remote terminal. Aspen usually has the line length as well, which is a useful thing to know, but it really isn't critical to our protection calculations. As I mentioned the other day, the relays can take the line impedance and the measured fault impedance and give a pretty accurate estimation of where physically, the distance that the fault is from the station. So that can be used to inform crews after a permanent outage, to give them an idea of where to start looking, so they don't necessarily have to drive or walk the full 14 miles of this line to find the problem to be able to fix it. We're also going to need some system data, so we need to know the voltage, the operating voltage, and we're going to need to know the line rating. So as we talked about with loadability, we've got a variety of ratings that we'd be working with. And in this case, we're going to be looking at the winter long-term emergency rating, which is a 4-hour rating. This is how long the system operators can operate the line at this, at this level before it's going to cause damage to the equipment. So this is how far they can push it for 4 hours. And you'll see that there's other ratings as well. There's usually a long-term rating or a short-term rating that might be, a 1-hour rating, or even a drastic action limit that's oftentimes in the 15 minutes or so rating. But there's a bunch of different definitions for these. But in this case, we're looking at our long-term emergency rating of 300 MVA. We're also going to have CT and a PT connected to the relay that provides our voltage and current measurements that the relay uses to calculate the apparent impedance seen by the relay for fault or non-fault conditions. So we're going to need to be able to use the CT and PT ratios to translate our per unit data into primary impedance data, and then eventually into secondary values, which is what the relay is going to measure, and what you typically set your relays based on is that secondary value. So you're going to have to step through these instrument transformer ratings to get there. So the first thing we need to understand is the line impedance itself. And we're going to need to calculate that. And like I said, we're going to need to take the per unit impedance we get from Aspen. We're going to need to convert that to primary ohms and then to secondary ohms. I just realized there's an error on my slide here. It should be just ohms primary for the Z base. That's converting from per unit to primary. So might want to make a note of that on your slides there, and I'll see if I can fix that and get a revised copy out. So basically, just like we would with any other per unit conversion, we're going to need to define our per unit bases. So we've got a voltage base, a line-to-line voltage base of 115 kV. Aspen is generally programmed at 100 MVA base. And we can use that to calculate our Z base, which we can use to convert from per unit back into ohms. And we know what our impedance is from Aspen. So we'd use the Z base and our per unit impedances to calculate to convert from per unit to ohms primary. And then from there, we can use our CT ratio and PT ratio to convert that into ohms secondary. So usually when we're working with Aspen, it's programmed in a rectangular format with R plus JX as your input parameters. When we're talking about the relay, we're usually looking at magnitude and angle, because that's, when you're looking at those RX plots and we're plotting out a line impedance, or we're plotting the relay operation, we're talking about our distance reach as a magnitude, and we're talking about our maximum torque angle as the angular quantity. So usually what we'll do is we'll convert it down into the polar representation with magnitude and angle, rather than continuing to work in the rectangular format. So we do the same thing and do the same calculation approach to get our positive and zero sequence impedance magnitudes and angles. Conveniently, all of our numbers that we started with ended up on nice round even numbers, 2.5 ohms secondary for the positive sequence impedance magnitude in 80 degrees, and 8 ohms secondary and 70 degrees for our zero sequence quantities. So this is what we'll use as a basis for the calculation for our zone settings. You can see over here, we've got some philosophies on how to set those. Zone 1 set at 80% of the impedance, and zone 2 set at least 120%. And there's some range on these. It's nothing that, every application is done exactly the same way. So this 80% could be 70% or less if you've got a very short line or some other reason, or it could be as much as 90% if you want to really push the accuracy of your modeling and CT performance and other errors that you could have as part of your system. Similarly, zone 2 is usually 120% is kind of the minimum, but I've seen utilities apply 150 or more percent margin or factor to a zone 2 element before, pretty commonly, and just depends on the utility's philosophy and their typical practices, because they generally try to set things very consistently from site to site. So coming up with a phase distance zone 1 and zone 2 reaches becomes fairly simple. We've calculated our zone 1 magnitude or the positive sequence impedance magnitude of a line at 2.5 ohms secondary, and we just pick a value at 80% of that, and you get 2 ohms secondary, and that's going to drive the relay reach that we've got shown here, that you're going to be having enough margin that you're going to be confident you'll be under reaching the remote terminal, which allows you to operate with no delay. And then your zone 2 element will be set above that. So we've got a similar factor here. We're using 120% in this example. So we take the line impedance magnitude and apply that 120% factor, and we've got 3 ohms secondary for our zone 2 setting, and that'll define the basically the size of those Mo characteristics, the circles that we use to graph this against the line impedance. Because zone 2 overreaches this remote bus, it'll see faults on the bus or on the beginning parts of these next lines. We need to set that with a delay to allow the protection at the remote station to operate to clear a fault, on an adjacent transmission line or some other piece of equipment that's outside the zone. So, typically, we'll see anything from 15 to 20 cycle delay. So about 1/3 of a second, 1/4 to 1/3 of a second, to delay this element. And that gives the protection at the remote end time to detect the fault, make a logical operation, close its output contacts to trip the breaker, the breaker to trip and clear, plus a good amount of margin to allow all of that to happen before this relay trips on. So, right there with some fairly basic calculations, we're able to set our zone 1 and zone 2 protection elements. In this case, as I mentioned, a lot of cases we aren't really setting that zone 3 remote backup element very often. So we can, I left it off this calculation example, but that'd be another thing that, we would look at and typically do a little bit more analysis in Aspen to really figure out, what the worst case remote bus fault was to get there. These calculations are fairly straightforward. So now that we've come up with our suggested set points, we need to do some other checks and verification to make sure that the elements are going to coordinate properly. So one of the checks that we do with that is check that our zone 2 element, so this overreaching element, does not overreach the remote line zone 1, because we've got this element delayed for, let's say, 20 cycles. If it overreaches the remote zone 1, it's going to be operating at the same time as that remote line's zone 2 protection, which probably is also programmed at that same 20 cycles. So now both of the relays will be operating with the same time delay for the same fault. In which case we really have lost coordination, and we've lost that selectivity of our protection scheme. So it's an important thing to check is take a look at our the reach off of the relay and compare it to that zone 1 reach that may be reaching further than this overreaching element, or it might be shorter. If you've got a really long line for line 1 and a very short line for line 2, you can certainly be in a scenario where you would where the zone 1 20% margin is overreaching the remote element. So there's a couple ways we can go about checking that. The first thing we got to consider is what's our worst case for that. So if we've got 2 lines at the remote station, we need to take one of the lines out of service, or if you have multiple lines, we need to take our strongest source out of service, because if you've got a fault source both from station 1 through line 1 and a fault source coming in through line 3, it's gonna impact the apparent impedance seen by the distance relay that we're trying to set. So typically what we'll do is try to think of the worst case single contingency, which is taking one of these lines out, and then do the evaluation to see where that zone, the zone 2 boundary is compared to the zone 1 boundary of the other line. So there's a couple ways to do this. In typical practice, what we do is we'll use Aspen to validate this. We'll run a fault along line 2. We will run fault every 1 or 2% of the line and move the fault down the line and see when does that zone 1 element stop operating, the line 2 zone 1 element. And that may be at 70 to 80% of the line, based on the typical 80% setting for a zone 1 element. And we'd stop at when we hit the end of that zone 1 reach. And we look at what is the apparent impedance measured at this terminal. And we would know that that is the impedance that the relay is going to see, when you're at the end of that remote zone 1. So that's what I've got here. So we run that fault in Aspen, and at the line 2 zone 1 boundary with line 3 out of service, we would get a value of apparent impedance seen by this relay. and we would convert that into a secondary quantity, and we compare that to the proposed zone 2 reach. So in this case, for a fault at the end of the line 2 zone 1 boundary, so when its zone 2 element's going to start operating, we measure 4 ohms secondary at this relay. And since that's a larger value than our setting of 3 ohms, and to operate, we need to have a lower value, the zone 2 is not going to, sorry. I messed up that spelling. Get back into here somehow. There we go. Because that calculation now shows that our zone 2 element in this relay is not going to operate for that fault. And we do the same thing for each line off the bus to validate that, this zone 2 element is not reaching further than it needs to, or it needs to be slowed down. So that's the way we typically go about it using Aspen. Is we'll use the intermediate fault command. We'll run a bunch of faults along the line. We'll figure out where that element stops operating, and use the calculated apparent impedance from the relay terminal to do it. The other example you can do, which is going to be very similar to what you have in your homework, is you can do it manually if you've got a fairly simple system. So if you take this line 3 out of service, now you've got the line 1 impedance, and you've got the reach of the zone 1 on line 2, and you can sum those together to figure out, what the impedance is between that, that point where the zone 1 stops operating and the relay. And then you can compare that to the zone 2 set point here. So what happens if you are in a case where your zone 2 element of the relay or setting is going to overreach a remote zone 1? And you've got a couple options there, and it goes back to that philosophy of either coordinating through sensitivity or coordinating through time delay. So, the first option would be to reduce the reach of that zone 2 element. Maybe you're fairly close, and you can just pull back the reach of the zone 2 from 120% to 115%. That's something you could do. But typically what we end up doing in that case is we go the other route, and we use a longer time delay, so that the zone 2 for line 1 here, because it's going to overlap with the zone 2 of line 2, or whichever line it's overreaching, we'll set a longer time delay to allow this zone 2 to coordinate with that one. So this zone 2 is set at 20 cycles. You might bump this one from 20 up to 40 cycles. That would provide that additional time delay you need to ensure that you're maintaining coordination between the two line terminals.
Hey, Brandon, I had a question for you.
Yeah.
So I've been following along. I've been hoping the revelation would hit me, but so when you say, and I'm looking at zone 2, 120% minimum, but less than the shortest remote zone 1. Mm-hmm. So I guess it's not clear to me. Do all of these breakers have their own relays, and then what is not being shown or additional zones?
Yeah. So for simplicity's sake, I drew in the one relay that we're setting, mm-hmm. But each of the locations, basically each of these breakers would have a line relay looking into the line. So in the case of line 2, this 52 breaker here would have a distance relay looking into line 2. And if we go back up to these time distance diagrams, Here's kind of what I'm talking about when I'm talking about the zone two
Okay.
reach.
Okay.
So, you know, if this is line one and then this is line two, you can see in this case, your zone one's operating at zero, zero delay. Your zone two is this first step, operating in about 0.3 seconds. And then in this case, we had a zone three, but basically this point here is where that zone two would stop operating. The case we're looking for here would be if this zone two was set much longer. Let's say it was set so it saw faults all the way towards almost to station three here, just because of how it was set. You'd end up in a situation that relay for a fault, let's say near station three, here on the side, your station two, zone two element would be operating 0.3 seconds. But if the station one relay here also reached that far, they'd both be operating in that same time delay. So you'd have, for that fault, both relays would trip, and you'd not only trip off line two, but you trip off line one as well for that same fault, which is what we're trying to avoid.
I understand. Okay, thank you.
So that's why, if we got to check for that scenario, because the line lengths and things like that can be different. You can have a really long line next to a really short line, and then if you do run into that case, you either need to pull the reach back so that you have some amount of coordination with your the sensitivity of the element. It'll stop operating before you hit that the end of that remote zone one reach. Or you've got to increase the timer. So if you increase the timer, you would be, basically set it to maybe 0.6 seconds. And then, that would jump up here and go straight across at 0.6 seconds. But then you have that time coordination in that case.
Hey, Brandon, can I just add one thing too, just for clarification? So what Blaine asks is if there's one relay per breaker, there can be hundreds of relays to trip a breaker. So typically the relay is responsible for doing a line protection element or a breaker failure type thing, but you can have many different relays that actuate and trip a breaker.
That's a great point. And usually when we're looking at step distance protection, we're looking at a step distance scheme coordinating with another step distance scheme. You certainly could have other types of protection off your remote terminal. You still have to meet the same objective of, we don't want our relay at station one tripping for a fault on a line out of station two, or some other time delayed protection element. We have to do the same type of coordination to make sure that we're maintaining that selectivity in our protection scheme. So, great question there. So one of the other things we're going to look at is loadability. So we talked about this briefly towards the end of last class. We've got a NERC PRC23 loadability criteria we need to meet for the transmission system. So in effect, what we're looking at here is we're comparing the line rating and using that to calculate an impedance point at 30 degrees. To say this is how far we need to be able to load the relay, and then we calculate, based on that Mo characteristic, we calculate what the impedance is of the relay at that point and make sure they don't overlap. So on the slide up here, we could see that the point at the corner of this load region would be the first calculation. This is as far as we want the relay to be able to see, so that we can say it won't operate through load. And then the value that is right here, where the boundary of the relay characteristic hits that 30 degree mark, is what we're checking it against. So we've got some calculations we can do. Just find my, no, I went way past. All right, here we go. No, almost. There we go. So we got some calculations so we can do to basically calculate those two impedances, you know, one for the boundary of the load region and one for the boundary of the relay. And, you know, ideally the relay's loadability, the relay reach will be less than that loading point. And, you know, that'll tell us if we've met our loadability compliance requirement. And if not, we've got to use load encroachment. So I went through this calculation here. We've got 300 MVA here. Basically use that to calculate the current through that's represented by 300 MVA. We've got the criteria for loadability for 4-hour rating uses a 0.85 per unit voltage. So that's this factor here. These are voltage. And we need to be able to load it up to 1.5 times that 4-hour rating. So that's that 1.5 factor there. And that turns out an impedance that we can use to then compare to the relay reach at that same point. So for the relay side of it, we're using ZLR, which is really actually the largest of your distance reaches. So in this case, that would be 3 ohms, which is our zone 2 phase distance element. We convert that into primary quantities using the PT ratio divided by the CT ratio. And then we need to evaluate it at the angle, at the 30-degree angle. And this Z1 angle here is our line angle, which would also be our maximum torque angle of the element. And the output of that provides an impedance. So this is the relay impedance magnitude at 30 degrees. So it's that point along the 30-degree line where the relay will stop operating. And this top one is the loadability point of where that load region would end at that 30-degree. That's actually circular, so it's at any degrees, but 30 degrees is the one we're evaluating here. And as long as your relay reach at 30 degrees is less than your relay load at that same point, you've met your loadability requirements, which in this case we have. So we don't need to do any other actions to imply load encroachment or adjust our elements or do anything like that. So the last calculation we're going to do is we've gone through and we've done this analysis. We've calculated our phase step distance scheme. We calculated our zone 1 reach or zone 2 reach. We set our time delays. We validated coordination with remote protection. We validated loadability. So our phase distance elements are now, we've gone through the calculation approach to say that, okay, this is what we're going to set our phase distance elements at. Now, if you recall from a couple classes ago, phase distance elements are only going to operate for phase faults. So line-to-line faults, 3-phase faults. We've got to set separate elements to respond to ground faults. So your single line to ground, 2 line to ground faults are going to operate off a different operate quantity. So we need to set those independent. What most relay manufacturers do is to keep it consistent and easier for someone to understand the relative reach of phase distance elements versus ground distance elements, is they set the ground distance elements using the positive sequence line impedance values in the same way that we set the phase elements. And then they apply a zero sequence compensation factor that the relay uses to internally scale up or down the positive sequence values to the appropriate zero sequence value. So each relay has a little bit different way of approaching this. We're talking mostly about Schweitzer relays in this class, and those are certainly the most commonly applied in the US, so I think it's appropriate to use those for this example. But they use this K01 factor here to address this within the relay. And it's, it's a calculation that uses zero sequence impedance minus the positive sequence impedance divided by 3 times the positive sequence impedance, the polar quantity using both the magnitude and angle. So that allows us to set our ground distance elements with the exact same reaches as the phase distance elements. We'd likely have to do some additional checks and analysis to make sure we're maintaining the same coordination and things like that between remote terminals and remote relays. But for most cases, you're able to just directly set your ground distance element equal to your phase distance element for zone 1 and zone 2. So we'll have that same reaches. And then we'll use our positive and zero sequence impedance values from the line impedance values to come up with this K01 factor, and that drives the settings that we put into the relay to allow the relay to know how to adjust these positive sequence values into zero sequence values when because they're actually operating on zero sequence quantities rather than positive sequence quantities. So it's kind of a handy thing that the relay manufacturers typically do to make things a little bit easier for us as relay engineers being able to look at the phase distance elements versus the ground distance elements and have a rough idea of how far their reach is, because otherwise you'd end up with something that your zone 1 phase would be set at 2 ohms and zone 2 ground or zone 1 ground might be set at 6 or 7 ohms, which is technically correct, but it makes it a little harder to just visually look at your settings and say are my settings consistent as far as the reach, the phase and ground reach. So that's basically all you got to do for your very basic step distance settings example. So this is the same calculations we would go through as practicing relay engineers when we go to approach a line protection package. Usually we've got a lot more validation and modeling these and looking at how they respond compared to the rest of the system in Aspen. But the base calculations to get to the proposed set points are here, and usually we go through the same calculation and then we really put it through its paces in simulation using Aspen. And usually we're not changing anything because these fairly basic calculations work pretty well at providing reliable and selective protection. So any questions on the calculation example?
Randy, could we look at the impedance relay 30 max formula one more time? I wanted to make sure I understood what the 0.85 and 1.5 were.
Okay, yeah. So actually, I'll go up to this one because I think I've got a better slide that shows it. Okay, here. All right. So the NERC requirement says that okay, so it checks to see that the relay will not operate for 150% of the highest facility ratings. So that's that winter LTE, long-term emergency rating, and 85% voltage. So you reduce the voltage, which impacts how the relay responds and how the load looks, and at a 30-degree angle. So that's where those 3 numbers are coming from. It's right out of the PRC 23 compliance. And probably if you're going through that math and looking at, okay, I'm taking the cosine of the line angle, which is this value here, and subtracting that 30-degree value off of it, this is where to look to kind of get where that calculation's coming from. And basically what we're trying to do is, calculate a point like this loadability limit that they have shown with a X on it at the, corner of this triangle. That's what we're trying to say is this is our relay, how far our relay is going to reach at that angle. And it's the magnitude ZL here that is the loadability limit.
It's the Sakatoa, essentially, right? It's the adjacent of that angle. So that's why you got to use the cosine of the angle between the two. So you're literally just getting, if you're at 30, at 30 degrees, what is that point going to intersect the Mohs circle? So that's why you need to calculate the ZL. And it literally is just a right triangle. So you can use a trig identity.
Yeah. So you're using your trigonometry to figure out what the ZL quantity is. And then the other calculation is coming up with, this gray shaded region here. What's the impedance from the origin to this, this characteristic? And if you plotted it at any angle, and said, okay, my power can flow at any angle and whatever, it would make a circle around the origin. So the other calculation that you're doing is looking at, what's this impedance point, at the quarter of this loadability limit, and then you're comparing those two values. And this is kind of a deceiving, picture here, because they'd actually both be evaluated at that same 30-degree angle for whatever reason, probably just to make it a little bit easier in the paper I borrowed this figure from. They just had a little gap there, but really that's what you're looking at. If your impedance reach at that 30-degree limit is higher than the one defining the impedance of this shaded loadability limit, then there's a chance your relay is going to operate under load, and that's when you have to do another step to try to secure your protection to prevent it from operating under that load condition.
Okay, thank you.
Okay. Well, I've got a bunch of other slides on this that have some good information on some other things that can be considered or need to be considered, factors that impact our distance protection. And I'm just going to breeze through this because I do want to go over a couple of things, at least, one example of a pilot scheme, because I think that's something that we do on almost all transmission lines these days is a communication assisted scheme. So, if you're interested, certainly I recommend reading through the remaining slides that go over, some of these different challenges like the line length and source impedance ratio, mutual coupling impacts, the impacts of infeed, power swings, some other things. I know I'll just quickly flip over that. Something happened to my figure there. It's not supposed to look like that. Oh, wow, did I didn't realize I added animations to that. Okay. So I know one of the other questions we had earlier was, what are these other characteristic shapes? We got the circular Mohs characteristic. Well, I've got a couple examples here in this slide. The one on the left shows a quad element. So you can see it's a rectangular element. You can control the reach along the transmission line, how far to look on the transmission line, but then you can make it wider so that you would cover a fault with fault resistance. You can see this point here. The lens characteristic is another one that is very uncommonly applied, but it is out there. They make relays that do this, and I've set a couple of them for preventing a relay from operating under a stable power swing condition. There's another NERC criteria, the PRC 26 that has some stuff having to do with power swing system stability type stuff. So that probably could go most of your career and not get into setting a lens characteristic. I certainly did. So, but it is out there, and there's some other types of characteristics that you can apply as well that I've never applied, but other options are out there if you've got to do something really clever with your distance protection. So I'm going to stop this slideshow from here, and then I'm going to move over to the one on pilot protection, which I am certainly not going to get through everything, but I do feel like that's a really important topic to at least get some information about, because it's a very commonly applied thing within the transmission system. We'll probably be able to cover some of the types of pilot schemes and what they are, and maybe go through one pilot example that I've got in the slides, and then the rest of it you can certainly look through on your own. So all stuff you'll have a whole career worth of time to learn about, and all the unique and interesting stuff if you do end up choosing to be a relay engineer by profession. You'll learn a whole lot about this stuff. So at least getting the concept out there, I think it's probably about as far as we'll get today. So skip over that because we've gone over this stuff a lot. So okay, so what is a pilot scheme? So it's a fairly generic term. But in effect, we're using a communications channel between the two stations to allow the line relays at one terminal to send information to the relays at the other terminal to improve the both relays' ability to detect an in-section versus an out-of-section fault. And the main goal with this is usually to improve clearing times of transmission faults. So, as we saw on the step distance scheme, there's a portion in the middle of the line, of a two-terminal line, where both terminals, zone ones, will likely see the fault. And for faults in that area, you're going to be operating instantaneously, so no intentional time delay, and you'll clear the line in 3 to 5 cycles. It'll be, you'll go from having a fault to the fault being cleared from the system that quickly. Well, as you get out of those zone 1 reaches and have a fault near one terminal or the other, one end of the line isn't going to be clearing high speed, because one end will be seeing it within its zone 1, and the other end will be seeing it in its time delayed zone 2. So the clearing for that fault is not going to be instantaneous. You're going to have that 20 to 30 cycle time delay for the zone 2 element to clear the fault. When we start looking at transmission systems, especially if you get up to 230 or 345 kV, clearing time in the system becomes very important. If you leave a fault on the system for too long, you can cause system instability. You can have wider issues that then have cascading failures, can lead to blackouts and other problems. System operators and planners do studies to determine what an appropriate and acceptable clear time of the system is, and it can be very fast, and oftentimes has to incorporate things like breaker failure protection and other things in there. And even with a failed breaker, oftentimes some of the fastest I've seen might require the relays to fully clear a fault for anywhere on the line in under 8 to 10 cycles, which is not possible with a step distance scheme where you've got the longer zone 2 delay that has to operate for some parts of the line. So there's a lot of different varieties of pilot schemes out there, but they all have that same goal of basically identifying in section versus out of section faults faster and allowing both terminals to clear relatively high speed to isolate the fault. And they do this using the communications channel. And that communications channel may be sending something as simple as a single bit of data from one end to the other to inform the remote relay of what the local relay is seeing, and then same thing in the other direction. Or it might be as complex as a full data stream of measured values from one relay being sent to the other relay to accomplish a more advanced type of scheme. And that's typically applied in parallel with your step distance scheme, your directional ground overcurrent scheme, switch on default protection. So you've got this other protection that's there all the time, but in parallel with that, we've got this pilot scheme that'll operate faster. And that's typically done in the case that you lose your communications or you have some other reason why the pilot scheme needs to be disabled or fails. You still have that other protection there to provide the time delayed clearing if necessary. So generally, pilot schemes come into kind of two main varieties. There are directional comparison schemes. So these are either permissive schemes or blocking schemes, or can be a direct transfer trip type scheme, or differential schemes. So typically these days this is line current differential, and that's the scheme where you're sending the measured currents from one relay to the other terminal over a more robust communications channel. And those currents are synchronized and lined up, and the relays can now calculate, is the current going into the line equal to the current going out of the line? If it is, you don't have a fault. If it isn't, Kirchhoff's current law is no longer being upheld, so the fault must be within the line, and you operate. Directional comparison schemes operate on a mixture or a combination of forward and reverse looking over and under reaching protection elements. These could be distance elements or directional ground overcurrent elements. But the basic premise of the scheme is one relay is telling the other relay, the fault is behind me, so don't trip really fast because the fault's behind me, it's not on the line. Or the fault is in front of me, so if the fault's in front of you as well, you should trip fast. It's kind of the two basic premises of your directional comparison schemes is one relay knows the fault's in front of or behind it. It's either on the line or on the system behind the relay. And so does the other relay. By sharing that one piece of information, it's the fault in front or behind me, allows the remote relay to make a more informed decision on something like its overreaching element. So we'll go through a couple examples of those as we move through here. So we've got a variety of communications channels we can choose from. So, obviously if we don't have any communications available, we cannot apply this scheme. So a lot of utilities over the last 10 to 15 years have been putting a lot of investment whenever they do transmission line work. I mentioned on the first class about the optical ground wire, OPGW wire, that's a ground conductor on a transmission line that has fiber optic cable inside of it. And that's a lot of utilities have been investing in that a lot to either have a direct fiber connection between two ends of a line or utilize those fibers in a multiplexer network to build out a more robust communications infrastructure for not only pilot protection, but your other data for SCADA and other systems that have to interface with the station, can all be using that same communication network. Prior to fiber optics becoming really the go-to choice when they're available, we've got a lot of other options as well. So leasing a telephone line from the phone company is an option. It's not as much of an option anymore because those dedicated leased, basically a twisted pair phone line between two sites isn't as much of a thing these days as phone companies are moving towards, fiber optics and things like that for their data as well. But you'll still run into those occasionally. We might have microwave systems. So you might see microwave towers that are point-to-point wireless communications systems. Again, those are not getting installed as much these days, where that same investment could be put towards fiber, which might be a better option in many cases. And then the one probably we do see quite often is power line carrier, which is coupling a high frequency communication signal over the phase conductors of the power line itself. And so, basically you'd have your 60 hertz signal, or not signal, your 60 hertz power flow through the line. And on top of that, you would inject a high frequency that would be sent from one terminal to the other, and can either use a on-off type signal or a frequency shifting type signal that can be then interpreted by a carrier relay at the other end of the line to send that single bit of data from one side to the other. So a lot of options here, a lot of stuff to consider when you're picking your scheme. So let's see if this. Okay, so I'm going to go over a couple examples of pilot schemes, and we probably won't get through all of them, but I at least want to show a couple of the common ones. So the first one's a permissive overreaching transfer trip scheme, or a POT scheme. And this is probably the most commonly applied directional comparison type scheme that we see used these days. And basically what it does, it's kind of in the title here. It's a permissive scheme. So this is the case where one relay at one terminal sees a fault in front of it and gives the other terminal permission to trip fast, because if the relay at breaker 1 here sees the fault in front of it, and this would be an overreaching element because it's a permissive overreaching scheme, it knows the fault is in front of it, and it'll say, so the relay at breaker 2 over that communications channel, it sends a single bit of information that says the fault is in front of me, and that's received by the relay at the other end. The relay at the other end, if it also sees a fault in front of it, it knows process of elimination, the fault is in front of the remote terminal and in front of me, it must be on the line. It can then trip once those conditions are met to allow the line to operate fairly high speed. It's a very fast type of scheme. And the same thing's going on in both directions. So both relays are sending that same information to the other terminal. So both terminals can make that same informed decision. So I'm going to go through an in-section fault example and an out-of-section fault example. So how does this scheme respond to a fault that is within the line? And then how does the scheme respond to a fault that's outside of them? So on the figure here, we've got the relay, we've got the transmitter and receiver for the pilot scheme. This could be a multiplexer network or a leased line, or any of those options. You don't need a overly robust channel, but you do need something that will be able to transmit information over the line when there's a fault on it. So carrier isn't a good option here. And we'll take a look maybe at a DCB scheme, which is another one that is more applicable for carrier. And then up here, this RO, this is their reach or overreaching zone at each of these. So this is kind of that distance diagram. So basically, we've got protection elements at both terminals that are overreaching the remote terminals. So the sequence of what would happen for a fault on this protected line is the fault occurs, the relay elements, the overreaching elements programmed to this scheme on both ends see the fault because it's within their zone. And this arrow kind of showing the zone of protection here. And the relays will then assert their logical bit to say there's a fault within my overreaching zone. That goes to, this AND gate on both sides, which is not yet satisfied because I have not also received a signal from the remote end yet. And it goes to the transmitter of our communications channel. So it's sending that bit of there's a fault in front of me to the remote end. So the communications channel transfers that information in both directions. So both sides are transmitting and receiving a permissive signal to the remote end. And then the logic processes at both ends. And the AND gate here saying that the fault is, within the overreaching forward zone. And I've received a signal from the remote end saying that it's within its zone. It processes that and will close the trip contact on the relay to operate the circuit breaker. So the fault goes away because both circuit breakers at both terminals have cleared the fault. And, all of this happened in the matter of cycles. So instead of waiting, a third to a half of a second to clear this line fault, which you would have had to with a step distance scheme, or potentially would have had to, you're clearing it in the matter of cycles because you do not have to wait for that timer to time out to maintain your selectivity of the line, because you're informing your scheme with more information than you had available with that step distance example. So for an out of section fault, we'll take a look at the same thing. So a fault occurs. In this case, it's on this bus off the remote line. So this could be on the bus, it could be off an adjacent line, like the fault example that we looked at. The local relay element at terminal 1 here sees the fault within its overreaching zone. So it's in front of it, it's within the zone of reach. But the relay at location 2, at circuit breaker 2 here, does not, because it's a reverse fault in that case. So it's blocked and it doesn't operate. It's not within this reach. And these reach arrows that I borrowed this from IEEE C37113, and really the reach is defined by the CT. So this should start here rather than starting at what looks like the bus. But either way, that this element is not asserting, so it does not pick up. The relay at breaker 1, because it saw the fault in front of it, is sending a permissive signal to the receiver at 2. That received signal is processed, goes into the logic. And because in the case of breaker 1 here, we see the fault in front of us, but we have not received a permission signal, a permissive signal from the remote end. This AND gate does not get satisfied and we don't trip the circuit breaker. And on the other side, we received permission from the other end to trip, but we do not see a fault in front of us. So this AND gate isn't satisfied and no trip is made. So for those two basic examples, you can see how you really improve the selectivity and reliability and security of the scheme, while also improving your operate time of the scheme, because you don't have to wait for a coordination timer, that zone 2 timer, to time out. So any questions on the POTT example? I think I can fit one more in. All right, I'm going to skip this next one. And we'll look at a directional comparison blocking scheme. So this is another variety of a directional comparison type scheme. In this case, it's directional comparison blocking. So it's similar in a way to the permissive scheme we looked at, but we're kind of looking at the opposite thing. So rather than giving permission from one terminal to the other to say you can trip fast because the fault is on the, I think the fault is on the line, we are blocking the remote terminal from tripping if we see a fault behind us. And this type of scheme has the advantage that you can use a carrier system over the protected line to as your communications medium, because the signal we're trying to get from one terminal to the other is the fault is not on the line, rather than the fault is on the line. If a fault's on the line, there's a chance you're not going to be able to get your signal through. So if we go through those same types of examples here for an in-section fault, we have the fault occur. In this case, both relays, similar to the other example, see the fault in an overreaching element and assert the logic within there to say that I've seen it. But we're not transmitting anything, because rather than transmitting a permissive signal, we're transmitting a block for a reverse looking fault. So because we have to get something to block the signal, we have to get the information from one terminal to the other to receive the block and process it. We need to wait a little while and allow that block to make it from one end to the other before we assert the trip for this scheme. So we've got this timer, TL1, that's our blocking coordination timer, that we set with some pickup on it that gives that blocking signal time to get from one terminal to the other. So in this in-section fault, we've got this AND gate is satisfied because we're not receiving a block and we see a fault in front of us. So the timer times out. And this is usually set to 2 to 3 cycles. It's fairly quick. Basically, we just need to look at the communications path and say, how fast can we get a blocking signal from one terminal to the other, and set it with some margin above that. So that, at this point, the timer's timing because we're not receiving a block. Blocking signals are transmitted if appropriate. In this case, they aren't, because we don't see a fault behind either terminal. And once the blocking coordination timer times out, the logic asserts to trip the appropriate circuit breakers. So in this case, both timers time out. We send trip signal both circuit breakers. Circuit breakers operate to clear the fault. And now the fault is cleared and the scheme kind of resets until next time we do it. If we look at the out-of-section fault example, which is really a more interesting one for this type of scheme, is we have that same bus fault. And the local relay elements operate. So for that same bus fault for the DCB scheme, the overreaching element at terminal 1 sees the fault because it's overreaching past the remote bus, and it sees that fault. And the reverse looking element at the blocking element at circuit breaker 2 also sees the fault because it's detecting faults behind the relay rather than in front of the relay. It's a reverse looking element. So the local elements assert. In this case, we've got our overreaching element driving logic here. We've got our blocking element driving logic to the transmitter. The blocking coordination timer starts timing here because this AND gate's satisfied. We've got no block being received yet, and we do have a forward element, our overreaching element asserted. So this timer starts timing, and then the blocking signals sent. So this could be a power line carrier system, or it could be some other type of communication system. And when that's received, because you now have a logical 1 on this input to the inverted input to the AND gate, the AND gate's no longer satisfied and your timer times out. So that's why setting this coordinating timer here faster or slower than whatever your worst case signal transmission time is important. So in this case, we've prevented this from operating. We reset the timer based on receiving the block, and it prevents that logic from operating. And correctly, in this fault case, no trip decisions made by this relay because it's not a fault within the protected line. So we've got about 5 minutes left. And I do have a few other examples of these pilot schemes in here. And you've got the slide decks and can take a look at those. But this is some of the type of stuff you'd really encounter quite a bit as a practicing relay engineer, looking at these schemes, diving into the details, seeing how they operate, how to handle unique scenarios. It's a mix of figuring out the logic, the communications path, the timing sequence, clearing time requirements, the distance element reaches and things like that to accomplish on these schemes. So they can get fairly complex, but it's also a really powerful tool as a relay engineer to be able to really fine tune some of those high level protection system objectives that we're trying to accomplish with our line protection of high speed operation, increased reliability with security and dependability. And in this case, we're really improving selectivity as well, because we're securing our element against operating for things that are out of section. As with any protection challenge, there's trade-offs. So obviously looking at this, this is a more complex scheme than what we're working with a step distance scheme. We require additional logic and timers and coordination between communications channels and things like that. So you're gaining all of that at the sacrifice of some additional complexity and additional cost, because you've got the same relays or potentially similar relays, but you also have the communications infrastructure cost, and additional complexity, programming and testing costs associated with this. So that really wraps up most of what I was hoping to cover with these classes on line protection. I hope you've gotten something out of it, and we'll learn more about this as some of you move into careers in the power system. You'll certainly see this type of stuff in application a lot, whether or not you're a relay settings engineer or anything else having to do with power system. Hopefully some of these concepts will come in handy in your career and give you something to learn a little bit more about. So we do have a couple minutes left. I'll open it up for any questions on what I've covered today or anything having to do with line protection. We'll wrap up from there. In the next class, we'll learn a little bit about some bus protection schemes.
Hey Brandon, I'm a little confused. Do you mind going over the blocking signal again?
Yeah,
Okay.
certainly. So the blocking signal is driven by this reverse looking element. So most of the distance elements and things we looked at were forward looking. So they would only operate for faults in front of the relay, in front of, in this case, being faults on the line or beyond the line. So in the case of this type of a blocking scheme, we're actually programming an element to look behind the relay. So it's not going to operate at all for a fault on the line, but it will see a fault behind. It'll operate for a fault in the reverse direction. Basically, your current is flowing, in the reverse angular relationship to the voltage that you would for a forward directional fault. So the basic premise of this scheme is, if the relay at terminal 2, in this case, knows that the fault is behind it, meaning the fault is not on the line, it can send that information to the relay at terminal 1 to say, block this scheme from tripping because the fault is behind my terminal. You know, this relay at 2 knows the fault isn't on the line because it's seeing it in the reverse direction. And by sharing that information, that blocking signal from one to the other, and again, it's just a logical bit, a 1 or a 0 we're sending. Normally, we're not sending anything, and then when this blocking element, reverse looking element, asserts because the fault is behind the relay, it sends a logical 1 to the remote end to block, this part of your trip logic from operating. It prevents this terminal from tripping for that fault. The terminal at circuit breaker 2 is already not tripping because it knows the fault is in the reverse direction and it's not on the protected line that the scheme is trying to protect. Does that provide some clarity to what you were looking for?
Yeah, thank you.
Okay. Any other questions on line protection or anything else? We're a minute over, so we can certainly call it a class and take it from there. But I'm open to hanging on if we get any other questions for folks. Well, all right. Well, I really appreciate the questions and interaction today, and hopefully was able to share some of the stuff about some of our some other types of line protection that you might see in industry, and we'll come back and talk on Thursday about bus protection, and that'll be my last class presenting. So really appreciate everybody's time, and look forward to talking to you on Thursday.
Thank you, everyone.
Thanks, Brandon.
Thanks.
Thanks, Brandon.